Hello! In this lecture, we will see how data preparation works as we pre-process data for one discrete variable. Discrete variables don't need fine classing or splitting into categories because they are already categorical by definition. For convenience, let's create working data frames for all the pre-processing. Let df underscore inputs underscore pre-processing be equal to lone data inputs train, and df underscore targets underscore pre-processing be equal to lone data targets train. Let's start with a rather simple variable, grade. We want to assess its explanatory power with respect to the outcome of interest, that is, being a good or a bad borrower. We also need the corresponding outcomes contained in the good-bad column. Now, we can create a new data frame called df1, where we will store only the independent variable grade from the df inputs pre-processing data frame and the dependent variable good-bad from the df targets pre-processing data frame. The values of the grade variable are letters from A to G. They represent external grades, A showing the highest credit worthiness and G showing the lowest. In this lecture, we will calculate the weight of evidence of this discrete variable. The formula was equal to the natural logarithm of the ratio of the proportion of good borrowers to the proportion of bad borrowers. Therefore, to find the weight of evidence of grade, we must first find the proportion of good and bad borrowers by grade. Let's start with the number of borrowers for each grade. To do that, we can count the rows that contain each of the grades. We do this with the group by method. Group by splits the data according to certain criteria. In our case, we want to split by grade, so we type df1.groupby, and in brackets, we refer to the grade column. Since we want this code to be reusable, let's parameterize it. We know that it is the first column in our data frame. Recall that counting in Python starts from 0, so the first column has index 0. In this case, we'll refer to the first column as df1.columns.values and 0 in brackets. If we group like this, the grouped values become indexes in the result we get. Having them as indexes is great, but rather limiting, so it's better to have them as ordinary values. This is something we must specify explicitly in the group by method by setting the asIndex parameter to false. We are actually interested in the number of rows, or the count the rows in each group. Here, we'll refer to the second column in our data frame, that is, the column with index 1. Since we want the total count of rows, we'll apply the count method. Let's run the cell. We've got a result that contains all grades in the first column and the number of rows for each of the grades in the second column. Another piece of information we may need is the proportion of good and bad borrowers are within each group. This can be summarized either by the proportion of good borrowers or by the proportion of bad borrowers. It doesn't matter which one, since the proportion of good borrowers equals 1 minus the proportion of bad borrowers. Let's calculate the proportion of good borrowers here. Remember that the good-bad variable has a value of 1 when the borrower is good and a value of 0 when the borrower is bad. Hence, we would get the proportion of good borrowers simply by calculating the average of good-bad. We can apply the same statement as above, except that at the end, we apply the mean method instead of the count method. Okay, now let's merge these two results into one data frame. You can see here that there are two columns with labels grade, which are exactly the same. So we can be certain that the results are matching after merging the two outputs. We don't need one of the columns, so let's overwrite df1, retaining all rows and only its first, second, and fourth column. The names of our columns are suboptimal, so let's change them to something more instructive. We keep the name of the first column. We'll rename the second column containing the number of observations to nobs. The third column containing the proportion of good borrowers to proportion good. And here is the clean result. Great! From now on, we'll only use these two columns in a series of calculations of weight of evidence and information value. By the way, let's calculate the proportion of observations that falls into each grade. It is the number of observations in each row divided by the sum of the number of observations in each row. First, let's calculate the number of good borrowers and the number of bad borrowers by grade group. We'll store the number of good borrowers in a variable called nGood. It is equal to the proportion of good borrowers multiplied by the total number of observations that have the respective grade. And we'll store the number of bad borrowers in a variable called nBad. It equals the proportion of bad borrowers, which is 1 minus the proportion of good borrowers, multiplied by the total number of observations that have the respective grade. Second, we calculate the proportions of good borrowers and bad borrowers for each grade. The percentage of good borrowers in the respective grade category equals the number of good borrowers in the respective category, divided by the total number of good borrowers, which is the sum of good borrowers in all categories. Similarly, the percentage of bad borrowers in the respective grade category equals the number of bad borrowers in the respective category, divided by the total number of bad borrowers, which is the sum of bad borrowers in all categories. Awesome! We have everything we need to calculate weight of evidence for the categories of grade. Let's store it in the WOE variable. It is equal to the natural logarithm of the ratio of the proportion of good borrowers to the proportion of bad borrowers. We'll use the NumPy function, nplog, to calculate the natural logarithm. And here we have it, the weight of evidence of the variable grade. It is useful to sort the result by weight of evidence, starting with the category with the lowest weight of evidence. In this way, we'll see the categories where borrowers have the highest default rate first. When I create PD models, I like to also calculate the differences in the proportion of good loans between two subsequent categories and the difference of weight of evidence between two subsequent categories. Usually, we don't need those, but it's good to have them just in case. We'll use the function diff to calculate them. Here, we'll get negative values because the function subtracts the value of one row from the value of the row above. It is more intuitive to see positive values, as they show how much weight of evidence would increase from one class to the next. This is why we'll take the absolute value of that difference. Finally, we can calculate information value. Let's store it in the IV column. The information value is equal to the sum of the proportion of good borrowers for the respective category minus the proportion of bad loans for the respective category, multiplied by weight of evidence for the respective category. The information value column is the same on each row because this metric refers to the information value of the variable grade overall. Good job! In the next lecture, we will see how we can automate this procedure.